Good day, all. Now that we have done our delta to star transformation, we are now going to look at the other way around where we've got a star system and we are wanting to convert it into a delta system. So what you see on the left hand side is your star system, on the right is the delta system where you're wanting to do the conversion to. And therefore, what you do in this instance again, you take your star system and you put it inside your delta system as in that case. So to make this more understandable, what I've done is I've removed the other two phases on my delta and left just the one phase, which is ZCA in this case. Now, in order for you to get the numerator of your fraction, you must multiply the ZA and ZB and then ZA and ZC and then ZB and ZC. So all of your star impedances must be multiplied to one another. You add up those multiplications as done on the formula at the bottom, and then it gets divided by the impedance that is on the furthest side of your ZCA. Or to say it in another way, it gets added to the impedance not adjacent to ZCA. All right. So in this case, that would be our ZB. Looking now at ZAB. Similar thing for ZAB. What you do with the numerator is still the same. You make sure that you multiply each of those impedances on your star connections and then add them up together. And then the bottom part is going to be made up of your furthest away impedance from your ZAB that you're looking at. Or to say it in another way, it's going to be the impedance that is not interconnected to your current impedance of your delta that you are trying to find, which in this case is ZC. Then we look at our last one where you're looking at ZBC. So again, here you multiply all of them, and then for your denominator, it's going to be ZA, which is the one that is not interconnected to nodes B and C, that ZBC is connected to. What I then want you to notice now with everything back onto the system is that once you have that multiplication over your furthest away or opposite impedance, you can simplify it further. So on ZCA, I've simplified it and it simply becomes your ZA plus ZC, ZCA. Do you hear that? So it's ZA and ZC. Then it's plus your ZA, ZC divided by your ZB. So a ZAB as well would be my ZA plus my ZB plus your ZA multiplied by ZB over your ZC, which was the one that was opposite. And so that's how you would go simplifying it further. But I don't want you to worry if you don't remember the simplest version and you have to do this. Then just know that you do the multiplication of all your numerators and you divide by the impedance that is furthest away from the one that you are looking at. So this is an example that is showing on the textbook that we're utilizing, where you have a three-phase system and it's a star connected load which has got an ABC rotation, so it's a positive phase sequence, and they want you to convert it into a delta connected load. Okay, and then once you've done the conversion, we want to find what our phase currents are and then calculate our star point potential. Now let's remember from Millman's that the star point potential is VSN. So I first just did so that I know my positive phase sequence, that's how it would look like. Remembering that my line voltages in a positive phase sequence usually would lead my corresponding phase voltage. So I draw now with the references I've been given, my VA, my VB, and my VC, so that I can be able to draw in my first line voltage, which is VBC in this case. We remember how to draw this, guys. You bring across the negative VC, then you draw your parallelogram, and your resultant will give me my VBC. How do I know it's VBC? It's between VB and my minus VC. I can then go ahead and throw in my other two voltages, which are going to be at 120 degrees from the one that I've already have. How do I name them? I simply follow the positive phase sequence convention. I've got a B already, VBC. So at the bottom, the one that's looking like a minus 90 degrees should by default be a VCA, and therefore the top one will be a VAB. I then put in at the bottom so that I can have all of my voltages, my line as well as my phase voltages. I can always have them as a reference there. And then I go and I put in my impedances. Okay, so there's my formula for my ZCA and my ZAB. Once I have those two worked out, I can calculate what my IAB is going to be, and then I calculate what my ICA is going to be. And once I have that, I can finally work out what is my line current going to be on the A phase, which is IAB minus ICA. And I utilize that in order for me to calculate what my VAS is, because now I've got a star over there, so I know that the voltage across will be VAS as is on my load side. It's no longer my VAN. So I calculate my VAS utilizing my IA that I've just worked out, and I can utilize my ZA that I had already in the given scenario. I then am able to work out what my star point potential is as VSN, which is going to be VAN minus my VAS. This then takes us to our second example, where you again have a delta star system consisting of your impedances that they give you on your load, and they give us that we've got a voltage EBA is equal to 440 volts, and it's a negative phase sequence. Now I want you to note the voltage is EBA, and remember how we name our voltages is EAB, EBC, and ECA. So if I have an EBA, it means by default that it's a negative EAB, which means that it's EAB at 180 degrees. So that is not there, but you must be able to see from the question and deduce what your EAB actually is. So they say that we must find or use your star delta conversion to calculate your currents drawn from the supply, and then calculate the voltage across each impedance in the load. So there I can go and draw in my negative phase sequence. I put in my voltages in there, and as I've said, your EAB is simply that EBA at the other side, okay? So it's at 180 degrees. And then I'm able to then go and put in what values or angles those are at. I then go to the bottom here where I'm now writing what my ZCA is, my ZAB, and my ZBC are going to be. And I calculate them because I've got all of those impedances. And once I've done that calculation, I can calculate what all of my phase currents are going to be, my IAB, IBC, and ICA. Then I will be able to work out what my line currents are, which are my IA, IB, and IC using the formulas that we have already learned and are comfortable with by now. Once I now have all of my line currents, I can be able to go work out the voltage across each phase that they've been asking for. And those will be VAS, VBS, and VCN. Okay, guys? So therefore, that is what you utilize to calculate them.